Learning objectives. In this chapter, the user would learn the following in detail. Simple Network Management Protocol (SNMP v1), Structure of Management Information, STD Management Information Base or MIBs, SNMP v1 Protocol, SNMP v2, SNMP v3. Network Management Functions, Fault Management, Fault Identification and Isolation, Event Correlation Techniques. Network Management Functions, Accounting and Performance, Accounting Management, Performance Management, Network Usage, Metrics and Quotas. Remote Network Monitoring, RMON, Remote Network Monitoring, etc. Accounting Management. The accounting management level, which might also be called the allocation level, is devoted to distributing resources optimally and fairly among network subscribers. This makes the most effective use of the system available, minimizing the cost of operation. The A level is also responsible for ensuring that users are billed appropriately. The domain used within another administrative domain is referred as an interdomain. Interdomain accounting packets, and session records will typically cross administrative boundaries. Real-time accounting. Real-time accounting involves the processing of information on resource usage within a defined time window. Time constraints are typically imposed in order to limit financial risk. Accounting server. The accounting server receives accounting data from devices and translates it into session records. The accounting server may also take responsibility for the routing of session records to interested parties. Accounting Management Architecture. The accounting management architecture involves interactions between network devices, accounting servers, and billing servers. The network device collects resource consumption data in the form of accounting metrics. This information is then transferred to an accounting server. Typically, this is accomplished via an accounting protocol, although it is also possible for devices to generate their own session record. The accounting server then processes the accounting data received from the network device. This processing may include summarization of interim accounting information, elimination of duplicate data, or generation of session records. The processed accounting data is then submitted to a billing server, which typically handles rating and invoice generation but may also carry out auditing, cost allocation, trend analysis, or capacity planning functions. Session records may be batched and compressed by the accounting server prior to submission to the billing server in order to reduce the volume of accounting data and the bandwidth required to accomplish the transfer. One of the functions of the accounting server is to distinguish between inter- and intra-domain accounting events and to route them appropriately. For session records containing a Network Access Identifier or NAI, the distinction can be made by examining the domain portion of the NAI. If the domain portion is absent or corresponds to the local domain, then the session record is treated as intra-domain accounting event. Otherwise, it is treated as an inter-domain accounting event. Accounting Management Objectives. Accounting management involves the collection of resource consumption data for the purposes of capacity and trend analysis, cost allocation, auditing, billing. Each of these tasks has different requirements. Trend analysis and capacity planning. In trend analysis and capacity planning, the goal is typically a forecast of future usage. Since such forecasts are inherently imperfect, high reliability is typically not required and moderate packet loss can be tolerated. Where it is possible to use statistical sampling techniques to reduce data collection requirements while still providing the forecast with the desired statistical accuracy, it may be possible to tolerate high packet loss as long as bias is not introduced. The security requirements for trend analysis and capacity planning depend on the circumstances of data collection and the sensitivity of the data. Additional security services may be required when data is being transferred between administrative domains. For example, when information is being collected and analyzed within the same administrative domain, integrity protection and authentication may be used in order to guard against collection of invalid data. In inter-domain applications, confidentiality may be desirable to guard against snooping by third parties. Billing. When accounting data is used for billing purposes, the requirements depend on whether the billing process is usage sensitive or not. Non-usage sensitive billing. Since by definition, non-usage sensitive billing does not require usage information, in theory, all accounting data can be lost without affecting the billing process. Of course, this would also affect other tasks such as trend analysis or auditing, so that such wholesale data loss would be still unacceptable. Usage-sensitive billing. Since usage-sensitive billing processes depend on usage information, packet loss may translate directly to revenue loss. As a result, the billing process may need to conform to financial reporting and legal requirements, and therefore, an archival accounting approach may be needed. Usage-sensitive systems may also require low processing delay. Credit risk is commonly managed by computerized fraud detection systems that are designed to detect usual activity, while efficiency concerns might otherwise dictate batched transmission of accounting data where there is a risk of fraud. Financial exposure increases with processing delay. Thus, it may be advisable to transmit each event individually to minimize batch size or even to utilize quality of service techniques to minimize queuing delays. In addition, it may be necessary for authorization to be dependent on ability to pay. Since in usage-sensitive systems, accounting data translates into revenue, the security and reliability requirements are greater. Due to financial and legal requirements, such systems need to be able to survive in audit. Thus, security services such as authentication, integrity, and replay protection are frequently required, and confidentiality and data object integrity may also be desirable. Application layer acknowledges are also often required so as to guard against accounting server failures. Auditing. With enterprise networking expenditures on the rise, interest in auditing is increasing. Auditing, which is the act of verifying the correctness of the procedure, commonly relies on accounting data. Auditing tasks include verifying the correctness of an invoice submitted by a service provider or verifying conformance to usage policy, service level agreements, or security guidelines. To permit a credible audit, the auditing data collection process must be at least as reliable as the accounting process being used by the entity that is being audited. Similarly, security policies for the audit should be at least as strict as those used in preparation of the original invoice. Due to financial and legal requirements, archival accounting practices are frequently required in this application. Where auditing procedures are used to verify conformance to usage or security policies, security services may be desired. This typically will include authentication, integrity, and replay protection as well as confidentiality and data object integrity. In order to permit response to security incidents in progress, auditing applications frequently are built to operate with low processing delay. Cost allocation. The application of cost allocation and bill-back methods by enterprise customers is not yet widespread. However, with the convergence of telephony and data communications, there is increasing interest in applying cost allocation and bill-back procedures to networking costs, as is now commonly practiced with telecommunications costs. Cost allocation models, including traditional costing mechanisms and activity-based costing techniques, are typically based on detailed analysis of usage data, and as a result, they are almost always usage-sensitive. Whether these techniques are applied to allocation of costs between partners in a venture or allocation of costs between departments in a single firm, the cost allocation models often have profound behavioral and financial impacts. As a result, systems developed for these purposes are typically as concerned with reliable data collection and security as are billing applications. Due to financial and legal requirements, archival accounting practices are frequently required in this application. Intra-domain and inter-domain accounting. Much of the initial work on accounting management has focused on intra-domain accounting applications. However, with the increasing deployment of services such as dial-up roaming, internet fax, voice and video over IP and QoS, applications requiring inter-domain accounting are becoming increasingly common. Inter-domain accounting differs from intra-domain accounting in several important ways. Intra-domain accounting involves the collection of information on resource consumption within an administrative domain for use within that domain. In intra-domain accounting, accounting packets and session records typically do not cross administrative boundaries. As a result, intra-domain accounting applications typically experience low packet loss and involve transfer of data between trusted entities. Inter-domain accounting applications may experience substantial packet loss. In addition, the entities involved in the transfers cannot be assumed to trust each other. Since inter-domain accounting applications involve transfers of accounting data between domains, additional security measures may be desirable. In addition to authentication, replay, and integrity protection, it may be desirable to deploy security services such as confidentiality and data object integrity. In inter-domain accounting, each involved party also typically requires a copy of each accounting event for invoice generation and auditing. Accounting record production. Typically, a single accounting record is produced per session, or in some cases, a set of interim records which can be summarized in a single record for billing purposes. However, to support deployment of services such as wireless access or complex billing regimes, a more sophisticated approach is required. It is necessary to generate several accounting records from a single session when pricing changes during a session. In most cases, the network device will determine when multiple session records are needed, as a local device is aware of factors affecting local tariffs such as QoS changes and roaming. However, future systems are being designed that enable the home domain to control the generation of accounting records. This is of importance in inter-domain accounting or when network devices do not have tariff information. The centralized control of accounting record production can be realized. For instance, by having authorization servers require reauthorization at certain times and requiring the production of accounting records upon each reauthorization. In conclusion, in some cases it is necessary to produce multiple accounting records from a single session. It must be possible to do this without requiring the user to start a new session or to re-authenticate. The production of multiple records can be controlled either by the network device or by the server. The requirements for timeliness, security, and reliability in multiple record sessions are the same as for single record sessions. Event correlation techniques. The most widely used techniques in the field of fault localization and diagnosis are expert systems. Expert systems try to reflect actions of a human expert when solving problems in a particular domain. The knowledge base imitates knowledge of a human, which may be either surface, which resulting from experience, or deep, which resulting from understanding the system behavior from its principles. Most expert systems use rule-based representation of their knowledge base. The fault localization, the inference engine usually uses a forward chaining inference mechanism. This executes in a sequence of rule firing cycles. In each cycle, the system chooses rules for execution whose antecedents or conditions match the content of the working memory. The classifications of the existing solutions include techniques derived from the field of artificial intelligence, rule-, model-, and case-based reasoning tools, as well as decision trees and neural networks, model traversing techniques, graph theoretic techniques, and the codebook approach. Rule-based systems. Expert systems applied to the fault localization problem differ with respect to the structure of the knowledge they use. Approaches uses the surface knowledge is referred to as rule-based reasoning systems. The research on rule-based fault localization systems addresses the structure of the knowledge base and the design of the rule definition language. The core knowledge may be understood as a generic or reusable knowledge. It is useful to identify an approximate location of a fault in a large network. Customized knowledge allows us to precisely isolate a fault from the selected group of system entities. Rule-based systems, which use the surface knowledge, do not require profound understanding of the underlying system architectural and operational principles, and for small systems. The rule-based reasoning contains the following sequence of operations. Knowledge base contains expert knowledge on problem symptoms and actions to be taken. If, right arrow, then, condition, right arrow, action. Working memory contains topological and state information of the network, recognizes system going into faulty state. Inference engine in cooperation with knowledge base decides on the action to be taken. Knowledge executes the action. Rule-based paradigm is an iterative process. RBR is brittle if no precedence exists. An exponential growth in knowledge base poses problem in scalability, problem with instability. If packet loss is less than 10%, alarm is green. Packet loss is greater than or equal to 10% and less than 15%, then alarm is yellow. If packet loss is greater than or equal to 15%, alarm is red. Solution using fuzzy logic. Rule-based systems possesses a number of disadvantages that limit their usabilities for fault isolation in more complex systems. The downsides of rule-based systems include inability to learn from experience, inability to deal with unseen problems, and difficulty in updating the system knowledge. Rule-based systems are difficult to maintain because the rules frequently contain hard-coded network configuration information. Rule-based systems are also inefficient and unable to deal with inaccurate information. The lack of structure in the system of rules typically makes it very difficult to allow reusability of rules that seem so intuitive in hierarchically built distributed systems. Another problem is that rule-based systems get convoluted if timing constraints are included in the reasoning process. Also, rule interactions may result in unwanted side effects, difficult to verify and change. Given the difficulties of techniques that rely only on surface knowledge, expert systems used in the field of fault localization usually include some form of deep knowledge that represents relationships among system entities. The system model may describe the system structure, that is static knowledge, and its functional behavior, that is dynamic knowledge. Model-based systems. In model-based expert systems, conditions associated with the rules usually include predicates referring to the system model. The predicates test the existence of a relationship among system components. The model is usually defined using an object-oriented paradigm and frequently has the form of a graph of dependencies among system components. A different model which represents structure knowledge of network topology templates selected in such a way that any network topology may be expressed as instances of these templates. For each template, all possible alarm patterns are listed along with fault diagnosis functions. Expert uses correlation tree skeletons describing cause-effect relationships between network events. The root of the tree is always a symptom. The leaves are possible symptom causes. The model-based approaches do not possess the disadvantages that characterize rule-based systems. They have the potential to solve novel problems, and the knowledge may be organized in an expandable, upgradable, and modular fashion. However, the models may be difficult to obtain and keep up to date. Regardless of the type of knowledge used by expert systems, the fault localization process is driven by an inference engine according to event correlation rules, which are usually defined using a high-level language. Rule actions typically allow alarm filtering, replacement, suppression, escalation, clustering, and generalization. They can also involve more complex repair or testing actions. Case-based systems. Case-based systems are a special class of expert systems that base their decisions on experience and past situations. They are well suited to learning correlation patterns. When a problem is successfully solved, the solution or its parts may be used in dealing with subsequent problems. They are resilient to changes in network configuration. However, case-based systems require an application-specific model for the resolution process. Also, time inefficiency may make them unusable in real-time alarm correlation. Decision trees are used as a representation of an expert knowledge to guide a user observing symptoms of failure toward locating the root cause of the problem. They allow a simple and expressive representation of the expert knowledge. However, their applicability is limited by the dependence on specific applications and the degraded accuracy in the presence of noise. Model traversing techniques. Model traversing techniques use formal representation of a communication system with clearly marked relationships among network entities. By exploring these relationships, starting from the network entity that reported an alarm, the fault identification process is able to determine which alarms are correlated and locate faulty network elements. Model traversing techniques reported in the literature use object-oriented representation of the system. One approach exploits the OSI management framework. Event correlation in model traversal techniques is usually event-driven. For every observed event, which is typically mapped into a model node, the model is searched recursively following the relationship links between managed objects. The actual fault localization algorithms may be quite different. In the process of fault localization, classes are merged whenever the events are occurred. They include all the traced down to the same managed object. To facilitate the search, certain event properties can be explored. For example, level the events occurred when the primary failure is the most likely at the lowest level. Event type are some events that are more likely to indicate primary failures than others. Severity of an event states that the more severe events are likely to have caused other events in the equivalence class. The origin of an event, which may provide explicit information if the event indicates primary or secondary fault. Other techniques combine fault localization with testing. During the model traversal, managed objects are tested to determine their operational status. The root cause is found when the currently explored malfunctioning object does not depend on any other malfunctioning object. In multi-layer models, first a horizontal search is performed in the layer in which failure has been reported. When a failing component is located, a vertical search carries the fault localization process to the next lower layer. In the lower layer, the horizontal search is started again. Model traversing techniques are robust against frequent network configuration changes. They are particularly attractive when automatic testing of a managed object may be done as a part of the fault localization process. Model traversing techniques seem natural when the relationships between objects are graph-like and easy to obtain. These models naturally enable design of distributed fault localization algorithms. However, they are inflexible in modeling fault propagation patterns. They are unable to model situations in which failure of a device may depend on a logical combination of other device failures. Graph theoretic techniques. Graph theoretic techniques rely on a graphical model of the system called a fault propagation model or FPM, which describes which symptoms may be observed if a specific fault occurs. The FPM includes the representation of all faults and symptoms that occur in the system. Observed symptoms are mapped into FPM nodes. The fault localization algorithm analyzes the FPM to identify the best explanation of the observed symptoms. Graph theoretic techniques require a priori specification of how a failure condition. Alarm in one component is related to failure conditions or alarms in other components. To create such a model, an accurate knowledge of current dependencies among abstract and physical system components is required. The efficiency and accuracy of the fault localization algorithm are dependent on the accuracy of this priori specification. Fault propagation models take the form of causality or dependency graphs. A causality graph is a directed acyclic graph GC of E and C, whose nodes E correspond to events and whose edges C describe cause-effect relationships between events. Nodes of a causality graph may be marked as problems or symptoms. Some nodes are neither problems nor symptoms, while others may be marked as problems and symptoms at the same time. Causality graph edges may be labeled with a probability of the causal implications. Similarly, it is possible to assign a probability of independent occurrence to all nodes labeled as problems. A dependency graph is a directed graph G equal to O and D, where O is a finite, non-empty set of objects and D is a set of edges between the objects. With each object, a probability of its failure independent of other objects may be associated. Every directed edge is labeled with a conditional probability that the object at the end of an edge fails, provided that the object at the beginning of an edge fails. A dependency graph of an example network is presented here. Note that the presented dependency graph models all possible dependencies between managed objects in the example network. In reality, the graph could be reduced based on information on currently open connections. Codebook correlation model. Fault propagation patterns in the codebook technique are represented by a matrix of problem codes that distinguish problems from one another. In the deterministic technique, a code is a sequence of values from open curly bracket 0 to 1 closed curly bracket. The value of 1 at the ith position of a code generated from problem Pj. It indicates cause-effect implication between problem Pj and symptom Si. In the probabilistic model, codes contain values from open square bracket 0 to 1 closed square bracket that represent likelihood of the cause-effect implication between a given problem and a given symptom. The codebook is basically a matrix representation of a bipartite causality graph that has been optimized to minimize the number of symptoms. That symptom have to be analyzed while still ensuring that the symptom patterns corresponding to problems allow us to distinguish between the problems. A correlation matrix derived from an example initial causality graph is presented by using the causality graph. The correlation matrix monitors capture alarm events. The configuration model contains the configuration of the network and the event model represents events and their causal relationship. Correlator correlates alarm events with event model and determines the problem that caused the events. Correlation algorithms based upon coding approach for event correlation. Problem events viewed as messages generated by a system and encoded in sets of alarms. Correlator decodes the problem messages to identify the problems. Fault identification. Fault diagnosis. Fault diagnosis has been split into two-step process: alarm filtering and correlation, and fault identification. First, the fault management system receives an enormous number of alarms that need to be filtered and correlated into manageable categories. Second, the categorized alarms are further analyzed and tests are initiated on network elements in order to identify the fault that is the cause of the alarms. A single fault in a large communication network may result in large number of fault indications or alarms are produced. This makes the isolation of the primary source of failure a difficult task. The problem becomes worse in cases of multiple faults. An approach for modeling this problem of fault diagnosis uses a graph-based network model. It takes various dependencies among the different objects in the telecommunication environment and a novel approach to estimate the domain of an alarm. Based on that model, an algorithm for fault diagnosis is designed and analyzes its performance with respect to the accuracy of the fault hypothesis it provides. The more complex processes of fault management include alarm filtering and correlation, fault identification, and correction. Many of these functions involve analysis, correlation, pattern recognition, clustering or categorization, problem solving, planning, and interpreting data from a knowledge base that contains descriptions of network elements and topology. Artificial intelligence technologies are ideal for these types of functionalities. Alarm filtering and correlation. Alarm filtering can be thought of as four processes: compression, count, suppression, and generalization. Compression is the reduction of multiple occurrences of the same alarm into a single alarm. Count is the substitution of a specified number of occurrences of similar alarms or alarm categories with a new alarm. Suppression is inhibiting a low priority alarm in the presence of a high priority alarm. Generalization is referring to an alarm by its superclass, where the superclasses are determined by domain experts. These four processes are well defined and can thus be achieved through the use of rules or the application of expert systems or ES. In addition to filtering, the alarms need to be correlated. Correlating alarms is a difficult task due to their inherent ambiguity. Even with large detailed amounts of data, there still exists a significant amount of uncertainties and or inconsistencies. In many cases, there is more than one reasonable explanation for the underlying cause of a group of alarms. For instance, the non-occurrence of a remote event may cause a device waiting for that event. It takes to timeout, with several possible causes for this. This possible lack for response, the device could be faulty, the response could be delayed due to congestion, or the local device timer could be faulty. The production of incomplete data due to crash recovery cycles is another problem area for correlating alarms. Some network elements may have built-in mechanisms to reset themselves when a local fault tolerance level has been reached. This can cause the destruction of important evidence needed to diagnose faults, and can indicate that all is well when the failure condition still exists, causing a crash recovery cycle. The complex process of correlation can be thought of as substituting a set of alarms that match a predefined pattern with a new alarm. As described above, this process involves ambiguous, incomplete, and inconsistent data and can be thought of as a pattern recognition problem. The filtering and correlation of alarms is the first step of fault diagnosis. The second step involves further analysis and identification of the exact cause of the alarms or the fault. This process is an iterative one where alarm data are analyzed and decisions are made whether more data should be gathered. For that, a finer-grained analysis should be executed or problem solving should be performed. Gathering more data can consist of sending tests to network elements or requesting network performance data. Problem solving requires expert knowledge, which consists of domain knowledge, that is, knowledge about the network elements and topology and typical faults, and meta-knowledge, that is, knowledge about how to diagnose faults. A symbolic artificial intelligence or AI technology such as ES or CBR, that is case-based reasoning, is ideal for achieving this functionality. Due to the limitations of expert systems, CBR is the better choice for fault identification. CBR systems are more robust than ES because they can handle new and changing data through their ability to use analogy, can learn from experience through the acquisition of new cases, can scale well to large knowledge domains due to the ability of their knowledge representation structures to collapse or merge into each other, do not require extensive maintenance, can critique or identify the goodness of a proposed solution based on simulations and or previous cases from the case library, can use a method of knowledge acquisition that is less time consuming than expert system rule development. Case-based reasoning is based on the premise that situations recur with regularity. CBR can be thought of an expert that applies previous experiences stored as cases in a case library. Thus, the problem-solving process becomes one of recalling old experiences and interpreting the new situation in terms of those old experiences. An important component of any CBR system, as with any knowledge-rich AI system, is deciding what the key attributes of a case are and on which attributes the cases will be indexed. Indices are combinations of the case's attributes or descriptors and are used to predict which cases are useful to the current situation. Typically, the front end of an application that uses CBR will have a graphical user interface or GUI that allows a user to easily input new cases without requiring any detailed understanding of the underlying CBR engine. The cases can be input in a free-form manner, that is, text, and are automatically indexed into the case library. A key benefit in using CBR systems is the ability to learn. One obvious method of learning is to add new cases with their new solutions and evaluation to the case library, emulating specialization. Another type of learning occurs because of the ability of CBR systems to collapse cases or parts of cases that have similar attributes or problem solutions into a single case, emulating generalization. CBR problem solving can be depicted as a 5-step process as shown in figure. Number 1. Retrieval. Number 2. Interpretation and adaptation. Number 3. Evaluation and repair. Number 4. Implementation. Number 5. Evaluation and learning. The first step is retrieving cases that best match the current situation or case. Thus, it is crucial to use an appropriate indexing method such as decision trees or nearest neighbor matching. Once a case is retrieved, it must be interpreted and then adapted. The interpretation process is a simple comparison between the retrieved cases and the current case. Adaptation is a complicated, domain-dependent process that uses rules to adapt the current case to the problem situation and propose an initial solution based on the similarities and differences. The next step is an evaluation and repair cycle where the proposed solution is evaluated through comparisons to cases with similar solutions or through simulations, and the solution is modified accordingly. After the CBR system has found its best solution, the solution is implemented and the results are evaluated. The resulting evaluation, solution steps, and problem context are entered into a new case, which is then indexed into the case library, allowing the system to learn. Fault isolation. In a communication network, a single fault may cause a number of alarms to be delivered to the network management center. Multiple alarms may be a result of fault reoccurrence, multiple invocations of a service provided by a faulty component, generating multiple alarms by a device for a single fault, detection of and issuing a notification about the same network fault by many devices simultaneously, error propagation to other network devices causing them to fail, as a result generate additional alarms. It may be argued that typically networked systems provide plenty of information necessary to infer existence of faults. The process of fault diagnosis usually involves 3 steps. Fault detection, a process of capturing online indications of network disorder provided by malfunctioning devices in the form of alarms. Fault isolation, also referred to as fault localization, alarm/event correlation, and root cause analysis. A set of observed fault indications is analyzed to find an explanation of the alarms. Testing, a process that given a number of possible hypotheses determines the actual faults. Fault isolation is a process of deducing the exact source of the failure or a root cause from the set of observed failure indications. The most popular fault isolation technique is alarm correlation, a process of grouping alarms related by having the same root cause. Fault localization or isolation is subject to complications resulting from complexity, unreliability, and non-determinism of communication systems. Some of the common problems that have to be addressed by a fault localization technique are discussed below. Fault evidence may be ambiguous, inconsistent, and incomplete. Ambiguity is observed by set of alarm stems that the same alarm may be generated as an indication of many different faults. Inconsistency results from a disagreement among devices with regard to the facts related to network operation. One device may have perception that a component is operating correctly, while another may consider the component faulty. Incompleteness is a consequence of alarm loss or delay. It is essential that a fault management system be able to create consistent view of network operation even in the presence of ambiguous, inconsistent, or incomplete information. A fault management system should provide means to represent and interpret uncertain data within the system knowledge and fault evidence. A set of alarms generated by a fault may depend on many factors such as dependencies among network devices, current configurations, and services in use. Since fault occurrence, presence of other faults, values of other network parameters, etc. Due to this non-determinism, the system knowledge may be subject to inaccuracy and inconsistency. Fault evidence may also be inaccurate because of spurious alarms, which are generated by transient problems. When spurious symptoms may occur, the management system may not be sure which observed alarms should be taken into account in the fault localization process. An event management system should be able to isolate multiple simultaneous related or unrelated root causes. The additional complication of fault localization results that different related and unrelated faults may happen within a short time period. The event management system should be able to isolate such problems even if they happen within a short time of one another and generate overlapping sets of alarms. A fault localization process should try to find the optimal solution according to some accepted optimality criteria. A single alarm may indicate different types of faults that occurred in different communication devices. Fault localization may be unable to give a definite answer. Some approaches combine fault localization with testing to enable resolving these ambiguities. These approaches usually tailored to locating specific network faults. In the general case, the lack of automated testing techniques makes it impossible to verify a possible answer in real time. Therefore, some existing techniques try to isolate a set of probable fault hypotheses that may be later verified on or offline depending on the available testing techniques. Preferably, a confidence measure should be associated with each formulated hypothesis based on some measure of goodness. This measure may be a probability that a hypothesis is valid, its information cost, etc. The optimality criteria may include the minimum size of the hypothesis set, the lowest cost solution, the lowest error probability, etc. Fault localization process in large networks. Fault localization process in large networks should be performed in a distributed fashion. Communication networks become more and more advanced in terms of their size, complexity, speed, and the level of heterogeneity. Processing large volumes of information necessary to perform fault localization in such systems would be computationally prohibiting. It is also impractical to assume that the fault localization process has access to the information on the entire system. Many researchers have concluded that the fault localization process in large networks should be performed in a distributed fashion. It is performed by a group of event management nodes with data and processing complexity divided among them. Each of the managers governs a subset of network hardware and/or software components within boundaries marked by protocol layers or network domains. Errors propagate horizontally between peer-associated devices within the same layer, otherwise vertically from upper layers to lower layers and vice versa between related services. They may cross boundaries of management domains. As a result, the fault management system may be provided with indications of faults that did not happen in its management domain. They may be unable to detect all symptoms of faults existing in its management domain. Therefore, distributed fault localization schemes are necessary that would allow the management nodes to reach the solution collectively. A fault localization process has to take into account temporal relationships among events. An important aspect related to fault localization is the representation of time. Events are related not only casually but also temporally. Therefore, the fault localization process has to provide means to represent and interpret the time associated with an event occurrence as well as a technique for correlating events related with respect to the time of the occurrence and duration. Fault localization techniques. Numerous paradigms were proposed upon which fault localization techniques were based. These paradigms derive from different areas of computer science, including artificial intelligence, graph theory, neural networks, information theory, and automata theory. The classifications of the existing solutions include techniques derived from the field of artificial intelligence, rule, model, and case-based reasoning tools as well as decision trees and neural networks, model traversing techniques, graph theoretic techniques, and the codebook approach. Fault management. Fault management is the component of network management concerned with detecting, isolating, and resolving problems. Properly implemented, fault management can keep a network running at an optimum level, provide a measure of fault tolerance, and minimize downtime. A set of functions or applications designed for this purpose is called a fault management platform. In a telecommunications network, fault management refers to a set of functions that detects, isolates, and corrects network malfunctions. The system examines error logs, accepts and acts on error detection notifications, traces and identifies faults, and carries out a sequence of diagnostic tests. When a fault is encountered in a network, A component sends notification to a network operator using protocols such as Simple Network Management Protocol and uses complex filtering systems to assign alarms to severity levels. A current list of problems occurring on the network component is often kept in the form of an active alarm list such as is defined in RFC 3877, the alarm MIB. A list of cleared faults is also maintained by most network management systems. Fault management can be active or passive. Passive fault management is performed by collecting alarms from devices when an error is encountered. Active fault management addresses issues by monitoring devices using certain tools to determine whether devices are active and responding. Applications designed for fault management systems are called fault management platforms. Fault management systems may use complex filtering systems to assign alarms to severity levels. These can range in severity from debug to emergency, as in the syslog protocol. Alternatively, they could use the ITU X.733 alarm reporting function's perceived severity field. This takes on values of cleared, indeterminate, critical, major, minor, or warning. The latest version of the syslog protocol draft under development within the IETF includes a mapping between these two different sets of severities. It is considered good practice to send a notification not only when a problem has occurred, but also when it has been resolved. A later notification would have a severity of clear. A fault management console allows a network administrator or system operator to monitor events from multiple systems and perform actions based on this information. Ideally, a fault manager system should be able to correctly identify events and automatically take action, either launching a program or script to take corrective action, or activating notification software that allows a human to take proper intervention, that is, send email or SMS text to a mobile phone. Some notification systems also have escalation rules that will notify a chain of individuals based on availability and severity of alarm. The main tasks of fault management systems can be divided into three stages. Stage 1. Fault detection, the process by which network fault indicators in the form of alarms generated by faulty network components are captured online. Stage 2. Fault identification, the process of identifying the most likely causes of the received alarms. Stage 3. Testing operation, the process of determining the actual faults that caused the network to malfunction. Important functions of fault management include definition of thresholds for potential failure conditions, constant monitoring of system status and usage levels, continuous scanning for threats such as viruses and trojans, general diagnostics, remote control of system elements including workstations and servers from a single location, alarms that notify administrators and users of impending and actual malfunctions, tracing the locations of potential and actual malfunctions, automatic correction of potential problem-causing conditions, automatic resolution of actual malfunctions, detailed logging of system status and actions taken, metrics and quotas, measuring the usage of network resources in order to distribute costs and resources, for example, monitoring the use of a server by users in a specific department and charging the department accordingly. The benefits of the accounting management process are we can enable the measurement and reporting of billing information for individuals and groups. This information can be used to bill those users, allocate resources, and computes the cost of transmitting data across the network. Billing users is essential in recovering costs of building and maintaining network. Accounting management assists in ensuring that distribution of charges is fair for quotas, and metrics can be used to ensure users have sufficient resources to do jobs. Accounting usage information can be used to decide when to install new equipments and allocate time on a time-shared computer. Also, it determines the cost effectiveness of technologies. Setting the metrics and quotas are the one of the operation performed by the accounting management. The accounting management involves the following steps of processes: gathering data about the utilization of network resources, setting usage quotas using metrics, billing users for their use of the network, using collected network statistics to assist in resource allocation. Gathering data. Time frame for data collection will depend upon storage capacity of devices. Information to be gathered includes the number of total transactions, total number of bytes or packets sent and received. This data can be collected by querying activity logs on individual hosts and gathering traffic counters of bridges, switches, or routers. Setting usage quotas using metrics. Metrics can be used to learn to what extent users network resources. As part of accounting management, you need to decide which resources to measure, collect metrics about their use. RFC 1272 discusses metrics and setting quotas. Metrics work with quotas to help ensure each user gets a fair share of network resources. Going over quota could be used to deny access to a resource, increase bill if over quota. Metrics can be a powerful tool for informing and guiding decision making at all levels of an organization. They can, however, be detrimental if not designed and implemented properly. In order for metrics to deliver value rather than distraction, they must be clearly defined, completely understood, and broadly communicated, as well as focused on the areas that are most important to the success of an organization. This article provides insight to key activities essential for the development, implementation, and management of effective metrics. Developing a set of appropriate meaningful metrics requires an iterative process focused on the specific needs of the organization. It is very unlikely that any predefined metrics provided by an article or software package will be the right set for our organization, program, project, or process. Culture, industry, maturity, and readiness for quantitative methods of measuring performance must all be factored into the development process. Before any metrics are adopted, must also have a process to define, develop, and educate the organization. Network usage. Network usage displays the amount of data sent and received by the network interfaces. Usage data is displayed in an easy-to-read bar graph. Drill down into the data by clicking or tapping the graph's bars. Network usage is also referred as the network traffic analysis. The network traffic analysis gives the information about the usage of the networks and also provides monitoring of network traffic to avoid congestion. In computer networking, network traffic control is a process of managing, controlling, or reducing the network traffic, particularly internet bandwidth, for example, by the network scheduler. It is used by network administrators to reduce congestion, latency, and packet loss. This is part of bandwidth management. Packet-based traffic analysis and network performance monitoring provides network managers with near real-time traffic visibility into network usage based on conversations, applications, users, and class of service. Traffic management gives the good performance by different steps of sequence of operations. Some of them are listed below. Understanding the use of the network. Understanding the requirements of users. Measuring how well user requirements are met. Making changes to improve the quality of service experienced by users. Monitoring the effectiveness of the changes. Monitoring network traffic is an effective way of measure demand and usage. Set of policies and mechanisms that allow a network to efficiently satisfy a diverse range of service requests. Tension is between diversity and efficiency. Traffic management is necessary for providing quality of service or QoS. Traffic management applications. Detecting and resolving congestion. Identifying and correcting performance problems. Identifying and mitigating security breaches. Planning for future growth and new applications. Billing for usage. Traffic monitoring system design considerations. Accurate. Qualitative traffic measurements. Measure all types of traffic. Data on how traffic is routed. Timely. Up-to-date view of entire network under all traffic loads. Monitor all of the time scalable. Monitor all the devices in the network. Monitor all speeds of link up to 1G, 10G, 40G, etc. Minimal impact on performance. switch or router CPU utilization, network overhead, low cost embedded implementation, encourage pervasive deployment, focus complexity in the central collector. Traffic monitoring system includes measurement, data collection, and analysis. The process of measuring and controlling the traffic on a network link so that overfilling the link can be avoided is called bandwidth management. It helps to keep the internet connection working fast and smooth. To manage bandwidth, traffic is measured, analyzed, and the cause for heavy traffic is identified. The network traffic control tool is used to avoid unwanted traffic and schedule bandwidth usage. Bandwidth monitoring software helps pinpoint your actual problem so that you can stop guessing and start resolving it. Bandwidth monitoring basically entails tracking the bandwidth usage of leased lines, network connections, network devices like routers, switches, etc., and the like. It measures the actual amount of bandwidth being used, for example, for billing purposes. It proactively traces usage trends, bottlenecks, and connectivity errors and make informed decisions on how to balance and route network traffic and decide what purchases are necessary to improve the flow of data within the network. Furthermore, a bandwidth monitoring software can also be used to alert administrators whether there are network load issues or breached bandwidth thresholds, etc. Performance management. Network performance management is the collective techniques that enable, manage, and ensure optimal performance levels of a computer network. Network performance management generally requires the performance and quality service level of each network device and component to be routinely monitored. Network performance management typically takes performance metrics from all across the network at a granular level. It reviews performance of the router to measure performance for each port. Network performance monitoring processes help in identifying performance bottlenecks, whereas network performance management ensures that problems are mitigated and the network is restored back to the required performance level. In addition to internal metrics, network performance management also reviews, analyzes, maintains, and manages performance from a user perspective. Key factors in network performance management include network delays, packet losses, throughput, packet transmission, error rate. Performance optimization is the ability to classify the critical applications and allow them first right of access, that is, quality of service. The performance management provides the tools and information that allows for the administrators to measure the performance level and the load of each equipment that make up the network infrastructure. The objectives are to measure and improve the level of the service provided, to facilitate and assist the analysis and diagnosis. The performance management system includes the following features: consolidated monitoring, monitoring in real time, with the accounting stream protocols NetFlow/SFlow, measure of service level protocols with ALS and AAS. Consolidated monitoring. Consolidated monitoring consists of measuring an indicator regularly and presenting its changes over time in a concise and accurate report in the form of a graph suitable to the indicator represented. Smart Report uses the SNMP to collect the value of the performance indicator from equipments. Equipment models. Smart Report bases its operation on a system of equipment model. For each type of equipment, there is a monitoring model. A router is not supervised in the same way as a firewall. The aim of the equipment model is to define the indicators to monitor and the reports to produce, to provide the reports immediately with the relevant and appropriate monitoring for each equipment. Without any knowledge of the SNMP protocol or the MIB of the equipment, reports to be supervised. Amongst the indicators available in the equipment model, we often find the most common indicators published by almost all the manageable equipments, for example, bandwidth used on the network interface or CPU load, as well as the specific indicators for the role of each device, for example, use of buffers on a router, packages droppers on a firewall, requests served on a web server, etc. With the passive monitoring, the equipment models also provide information about the SNMP traps in order to be able to recognize and interpret traps emitted by equipment. Real-time monitoring. For some indicators like traffic, CPU, temperature, RMON, Smart Report can allow a real-time monitoring. It presents the same information as the consolidated monitoring, but with much closer measures. The measurement step can be decreased by the least 5 seconds. It is an excellent complement to the consolidated monitoring when it comes to making a diagnosis on a current problem. Unlike the consolidated monitoring, the measurements taken by real-time monitoring are not recorded and consolidated in a database for exploration over a longer period. The measures related to the real-time monitoring are carried out directly by the administrator's workstation through a Java module loaded in the Smart Report interface. Note that a network access or SNMP to the equipment is necessary from the supervisor position used for this feature, and that all the indicators cannot be monitored in real time, including those requiring scripts on the appliance. Flows analysis and NetFlow/SFlow collector. Smart Report includes a NetFlow and SFlow collector, coupled with a powerful scanning and access list engine. The SFlow collector provides vision on our network flows with classification like top talkers, top protocols, etc. and graphs. Remote Network Monitoring (RMON) or Remote Network Monitoring. The Remote Network Monitoring or RMON MIB was developed to support monitoring and protocol analysis of LANs. The original version, sometimes referred to as RMON 1, focused on OSI Layer 1 and Layer 2 information in Ethernet and token ring networks. It has been extended by RMON 2, which adds support for network and application layer monitoring, and by SMON, which adds support for switched networks. It is an industry standard specification that provides much of the functionality offered by proprietary network analyzers. RMON agents are built into many high-end switches and routers. The Simple Network Management Protocol or SNMP defines both a framework and a specific protocol for exchanging network information on a TCP/IP internetwork. The general model used by SNMP is that of a network management station or NMS that sends requests to SNMP agents running on managed devices. The SNMP agents may also initiate certain types of communication by sending trap messages to tell the NMS when particular events occur. However, one fundamental limitation of the protocol and the model it uses is that it is oriented around the communication of network information from SNMP agents that are normally part of regular TCP/IP devices, such as hosts and routers. The amount of information gathered by these devices is usually somewhat limited, because obviously hosts and routers, they can't devote themselves to network management tasks. Thus, in situations where more information is needed about a network than is gathered by traditional devices, administrators often use special hardware units called network analyzers, monitors, or probes. These are dedicated pieces of equipment that are connected to a network and used strictly for the purpose of gathering statistics and watching for events of interest concerned to the administrator. It would obviously be very useful if these devices could use SNMP to allow the information they gather to be retrieved and to let them generate traps when they notice something important. To enable this, the Remote Network Monitoring or RMON specification was created. RMON is often called a protocol and RMON referred to as the TCP/IP network management protocols. However, RMON really isn't a separate protocol at all. It defines no protocol operations. RMON is in fact part of SNMP, and the RMON specification is simply a Management Information Base or MIB module that defines a particular set of MIB objects for use by network monitoring probes. Architecturally, it is just one of the many MIB modules that comprise the SNMP framework. RMON standards. The first standard documenting RMON was RFC 1271, Remote Network Monitoring Management Information Base, published in 1991. RFC 1271 was replaced by RFC 1757 in 1995, which made a couple of changes to the specification. RFC 2819, May 2000, updates RMON to use the new Structure of Management Information version 2 or SMI v2 specification that is part of SNMP v2 but is functionally the same as RFC 1757. Remote monitoring or RMON is a standard monitoring specification that enables various network monitors and console systems to exchange network monitoring data. RMON provides network administrators with more freedom in selecting network monitoring probes and consoles with features that meet their particular networking needs. An RMON implementation typically operates in a client or server model. Monitoring devices, like commonly called probes in this context, contain RMON software agents that collect information and analyze packets. These probes act as servers, and the network management applications that communicate with them act as clients. While both agent configuration and data collection use SNMP, RMON is designed to operate differently than other SNMP-based systems. Probes have more responsibility for data collection and processing, which reduces SNMP traffic and the processing load of the clients. Information is only transmitted to the management application when required, instead of continuous polling. In short, RMON is designed for flow-based monitoring, while SNMP is often used for device-based management. RMON is similar to other flow-based monitoring technologies such as NetFlow and SFlow because the data collected deals mainly with traffic patterns rather than the status of individual devices. RMON MIB hierarchy and object groups. RMON is a MIB module. It consists almost entirely of descriptions for MIB objects, with each having the standard characteristics belonging to all such objects. All the objects within RMON are arranged into the SNMP object name hierarchy within the RMON group, which is group number 16 within the SNMP MIB, that is MIB2, object 3, 1.3.6.1.2.1. So all RMON objects have identifiers starting with 1.3.6.1.2.1.16. This single RMON group is broken down into several lower level groups that provide more structure for the RMON objects defined by the specification. RMON uses a special MIB module, RMON 16, which fits into the overall SNMP object hierarchy tree. Under MIB/MIB-2.1 within MGMT2, just like other MIB object groups such as SYS1 and IF2. Within this group, which has the group identifier 1.3.6.1.2.1.16, are 9 subgroups of RMON objects. Table describes each of the RMON1 groups, showing for each its name, its group code, which is used as the prefix for object descriptors in the group, and its RMON group number and SNMP object hierarchy identifier. Table 222, SNMP RMON MIB object groups, RMON group name, RMON group code, RMON group number, full group identifier, description, statistics, Etherstats, 1, 1.3.6.1.2.1.16.1. Objects that keep track of network statistics measured by the device. Example, statistics include network traffic load, average packet size, number of broadcasts observed, counts of errors that have occurred, the number of packets in various size ranges, and so forth. History, ether history, 2, 1.3.6.1.2.1.16.2. The history group contains a single table object that controls how often statistical data is sampled by the probe. The additional ether history group is optional and contains extra ether specific information. It is contained logically within the history group. Alarm 3, 1.3.6.1.2.1.16.3. This group defines the parameters under which an alarm may be generated to inform an administrator of an occurrence of import. The alarm group contains a table that describes the thresholds that will cause an event to be triggered. Inside bracket, see the event given below. Hosts, host 4, 1.3.6.1.2.1.16.4. contains objects that keep track of information for each host on a network. Hosts top n, host top n, 5, 1.3.6.1.2.1.16.5. This group contains objects that facilitate reporting of hosts sorted in a particular way. The administrator determines how these ordered statistics are tracked. For example, an administrator could generate a report listing hosts sorted by the number of packets transmitted, showing the most active devices. Matrix 6 1.3.6.1.2.1.16.6. This group keeps track of statistics of data exchanges between particular pairs of hosts, so the amount of data sent between any two devices on the network could be tracked here. Since a large network could have thousands of such device pairs, to conserve resources on the probe, often only the most recent conversations between device pairs are kept in the management information base. Filter 7 1.3.6.1.2.1.16.7. This Harmon group allows an administrator to set up filters that control what sorts of network packets the probe will capture. Buffer capture 8 1.3.6.1.2.1.16.8. This group is used to allow a probe to capture packets based on particular parameters set up in the filter group. Event 9 1.3.6.1.2.1.16.9. When a particular alarm is triggered based on the parameters in the objects in the alarm group, an event is generated. This group controls how these events are processed, including creating and sending an SNMP trap message to a network monitoring station. The original Harmon standard was heavily oriented around Ethernet LANs. Probes can also gather and report information related to other networking technologies by using other Harmon groups created for that purpose. The best example of this was the definition of a set of groups specifically for token rings, which was defined in RFC 1513 in 1993. The Harmon 2 MIB adds 10 more groups. Protocol directory, list of protocols the probe can monitor. Protocol distribution, traffic statistics for each protocol. Address map, maps network layer IP to MAC layer addresses. Network layer host, layer 3 traffic statistics per each host. Network layer matrix, layer 3 traffic statistics per source/destination pairs of hosts. Application layer host, traffic statistics by application protocol per host. Application layer matrix, traffic statistics by application protocol per source/destination pairs of hosts. User history, periodic samples of user-specified variables. Probe configuration, remote configure of probes. Harmon conformance, requirements of Harmon 2 MIB conformance. Harmon alarms, events and statistics. Alarms and events are particularly useful constructs in Harmon as they allow the immediate communication of important information to a network management station. The administrator has full control over what conditions will cause an alarm to be sounded and how an event is generated. This includes specifying what variables or statistics to monitor, how often to check them, and what values will trigger an alarm. A log entry may also be recorded when an event occurs. If an event results in transmission of a trap message, the administrator will thus be notified and can decide how to respond depending on the severity of the event. However, certain groups are related, such as alarm and event, and some groups, such as statistics, are pretty much always implemented in all Harmon probes. Obviously, when Harmon is used, the network management station must be aware of Harmon groups and must allow a network management application to be run that will exploit the capabilities of the Harmon MIB objects. SNMP v2. SNMP version 2 or SNMP v2 is a revised protocol that includes performance and manager-to-manager communication improvements to SNMP. As with SNMP v1, SNMP v2 functions within the specifications of the Structure of Management Information or SMI. SNMP v2 offers a number of improvements to SNMP v1, including additional protocol operations. SNMP v2 and Structure of Management Information or SMI. The Structure of Management Information or SMI defines the rules for describing management information using Abstract Syntax Notation 1 or ASN.1 The SNMP v2 SMI is described in RFC 1902. It makes certain additions and enhancements to the SNMP v1 SMI specific data types such as including bit strings, network addresses, and counters. Bit strings are defined only in SNMP v2 and comprise 0 or more named bits that specify a value. Network addresses represent an address from a particular protocol family. SNMP v1 supports only 32-bit IP addresses, but SNMP v2 can support other types of addresses as well. Counters are non-negative integers that increase until they reach a maximum value and then return to 0. In SNMP v1, a 32-bit counter size is specified. In SNMP v2, 32-bit and 64-bit counters are defined. SNMP version 2C. In practical terms, v2c is identical to version 1, except it adds support for 64-bit counters are useful for interfaces. Even a 1 Gbps interface can wrap a 32-bit counter in 34 seconds, which means that a 32-bit counter being polled at 1-minute intervals is useless, as it cannot tell the difference between successive values of 30, 40 due to the fact that only 10 octets were sent in that minute, or 30, 40 due to the fact that 4294967306, that is 2 power 32 plus 10 octets were sent in that minute. Most devices support SNMP v2c nowadays and generally do so automatically. There are some devices that require you to explicitly enable v2c, in which case you should always do so. There is no downside. SMI information modules, the SNMP v2. SMI also specifies information modules which specify a group of related definitions. 3 types of SMI information modules exist: MIB modules, compliance statements, and capability statements. MIB modules contain definitions of interrelated managed objects. Compliance statements provide a systematic way to describe a group of managed objects that must be implemented for conformance to a standard. Capability statements are used to indicate the precise level of support that an agent claims with respect to a MIB group, and NMS can adjust its behavior toward agents according to the capability statements associated with each agent. SNMP v2 protocol operations. The get next, and set operations used in SNMP v1 are exactly the same as those used in SNMP v2. SNMP v2, however, add and enhance some protocol operations. The SNMP v2 trap operation, for example, serves the same function as that used in SNMP v1. It, however, uses a different message format and is designed to replace the SNMP v1 trap. SNMP v2 also defines 2 new protocol operations, getBulk and informRequest. GetBulk. The getBulk operation is used by the NMS for retrieving large amounts of data such as tables. This message reduces repetitive requests and replies, thereby it improves performance. InformRequest. The inform operation allows one NMS to send trap information to another NMS and receive a response. It is also used to alert the SNMP manager of a specific condition. Unlike acknowledged trap messages, inform request messages are acknowledged. This is done by a managed device. Sends an inform request to the NMS. The NMS acknowledges the receipt of the message by sending a response message back to the managed device. Transmission of an SNMP v2 message. The process of transmission of SNMP v2 message can be summarized through the following points. The PDO is constructed using the ASN.1 structure defined in the protocol specification. This PDO is then passed to an authentication service together with the source and destination transport address and a community name. The protocol entity then constructs a message consisting of a version field, the community name, and the result from step 2. This new ASN.1 object is then encoded using the basic encoding rules like BER and passed to the transport service. SNMP v2 message format. The format of protocol data units in SNMP v2 is described in RFC 1905 and is similar to that of SNMP v1. The format for all PDUs in SNMP v2 is the same except for the get bulk request PDU message. SNMP version 2 or SNMP v2p message format. The party-based security model is quite complex, but the basic messaging in this version is described through the definition of a management communication, which describes the source and destination party and makes reference to a context for the communication. The overall message format is described in detail in RFC 1445. This information is summarized in table. Table SNMP version 2 or SNMP v2p general message format. Field name, syntax, size in bytes, description. Version integer 4. Version number describes the SNMP version number of this message, used for ensuring compatibility between versions. For SNMP v2p, this value is 2. DST party, sequence of integer, variable, destination party, an object identifier that specifies the party that is the intended recipient of the message. SRC party, sequence of integer, variable, source party, an object identifier that specifies the party that is the sender of the message. Context, sequence of integer, variable, context, defines a set of MIB object resources that is accessible by a particular entity. PDU, variable, PDU, the protocol data unit of the message. Community-based SNMP version 2 or SNMP v2c message format. This version of SNMP v2 was intended to keep a new protocol enhancements introduced by SNMP v2p but go back to the simple SNMP v1 security model. As such, the defining document for SNMP v2c RFC 1901 specifies that its overall message format is the same as that of SNMP v1 except that the version number is changed. This is shown in the table. Table community-based SNMP version 2 SNMP v2c general message format. Field name, syntax, size in bytes, description. Version integer 4. Version number describes the SNMP version number of this message, used for ensuring compatibility between versions. For SNMP v2c, this value is 1. Community octet string, variable, community string identifies the SNMP community in which the sender and recipient of this message are located. PDU, variable, protocol data unit, the PDU being communicated as the body of the message. User-based SNMP version 2 or SNMP v2u message format. SNMP v2u was defined as an optional security model at the time that SNMP v2c was standardized. RFC 1910 defines the user-based security model and the message format described in table. SNMP v2 message header. SNMP v2 message headers contain two fields, version number and community name. The following descriptions summarize these fields. Version number specifies the version of SNMP that is being used. Community name defines an access environment for a group of NMS. NMS within the community are said to exist within the same administrative domain. Community names serve as a weak form of authentication because devices that do not know the proper community name are precluded from SNMP operations. SNMP v2 common PDU format. SNMP v2 specifies two PDU formats depending on the SNMP protocol operation. SNMP v2 PDU fields are variable in length as prescribed by Abstract Syntax Notation 1 or ASN.1. The following descriptions summarize the fields illustrated in. PDU type identifies the type of PDU transmitted, that is get next, inform, response, set or trap. The various PDU type and its value illustrated in table given below. PDU type value, PDU type 0, get request PDU 1, get next request PDU 2, response PDU 3. Set request PDU. 4. Obsolete. This is not used. 5. Get bulk request PDU. 6. Inform request PDU. 7. Trap V2 PDU. 8. Report PDU. Request ID associates SNMP requests with responses. Error status indicates one of a number of errors and error types. Only the response operation sets this field. Other operations set this field to 0. The various error status field values, error code and its descriptions are illustrated in table given below. Table SNMP version 2 or SNMP v2 PDU error status field values. Error status value, error code, description, 0, no error occurred. This code is also used in all request PDUs since they have no error status to report. 1. Too big. The size of response-PDU would be too large to transport. 2. No such name. The name of a requested object was not found. 3. Bad value. A value in the request didn't match the structure that the recipient of the request had for the object. For example, an object in the request was specified with an incorrect length or type. 4. Read only. An attempt was made to set a variable that has an access value indicating that it is read only. 5. Gen error. An error occurred other than one indicated by a more specific error code in this table. 6. No access. Access was denied to the object for security reasons. 7. Wrong type. The object type in a variable binding is incorrect for the object. 8. Wrong length. A variable binding specifies a length incorrect for the object. 9. Wrong encoding. A variable binding specifies an encoding incorrect for the object. 10. Wrong value. The value given in a variable binding is not possible for the object. 11. No creation. A specified variable does not exist and cannot be created. 12. Inconsistent value. A variable binding specifies a value that could be held by the variable but cannot be assigned to it at this time. 13. Resource unavailable. An attempt to set a variable required a resource that is not available. 14. Commit failed. An attempt to set a particular variable failed. 15. Undo failed. An attempt to set a particular variable as a part of a group of variables failed, and the attempt to then undo the setting of other variables was not successful. 16. Authorization error. A problem occurred in authorization. 17. Not writable. The variable cannot be written or created. 18. Inconsistent name. The name in a variable binding specifies a variable that does not exist. Error index associates an error with a particular object instance. Only the response operation sets this field. Other operations set this field to 0. Variable bindings serves as the data field of the SNMP v2 PDU. Each variable binding associates a particular object instance with its current value, open bracket, with the exception of get and getNext requests for which the value is ignored, closed bracket. The following figure illustrates the fields of the SNMP v2 get, getNext, inform, response, set and trap PDUs. PDU type, request ID, error status, error index, object 1 value 1, object 2 value 2, object x value x, that is variable bindings. Get bulk PDU format. The following figure illustrates the fields of the SNMP v2 get bulk PDU. Figure. The SNMP v2 get bulk PDU consists of 7 fields. PDU type, request ID, non-repeaters, max repetitions, object 1 value 1, object 2 value 2, that is variable bindings. The following descriptions summarize the SNMP v2 get bulk PDU consists of 7 fields. PDU type identifies the PDU as a get bulk operation. Request ID associates SNMP requests with responses. Non-repeaters specifies the number of object instances in the variable bindings field that should be retrieved no more than once from the beginning of the request. This field is used when some of the instances are scalar objects with only one variable. Maximum repetitions defines the maximum number of times that the other variables beyond those specified by the non-repeaters field should be retrieved. Variable bindings serves as the data field of the SNMP v2 PDU. Each variable binding associates a particular object instance with its current value, open bracket, with the exception of the get and getNext requests for which the value is ignored, closed bracket. SNMP security. SNMP lacks any authentication capabilities, which results in vulnerability to a variety of security threats. These include masquerading, modification of information, message sequence and timing modifications, and disclosure. Masquerading consists of an unauthorized entity attempting to perform management operations by assuming the identity of an unauthorized management entity. Modification of information involves an unauthorized entity attempting to alter a message generated by an authorized entity so that the message results in unauthorized accounting management or configuration management operations. Message sequence and timing modifications occur when an unauthorized entity reorders, delays, or copies and later replaces a message generated by an authorized entity. Disclosure results when an unauthorized entity extracts values stored in managed objects or learns of modifiable events by monitoring exchanges between managers and agents, because SNMP PDU type request ID error. Error index variable bindings does not implement authentication. Many vendors do not implement set operations, thereby reducing SNMP to a monitoring facility. SNMP interoperability. SNMP v2 is incompatible with SNMP v1 in two key areas: message formats and protocol operations. SNMP v2 messages use different header and protocol data unit or PDU formats than SNMP v1 messages. Furthermore, RFC 1908 defines two possible SNMP v1/v2 coexistence strategies: proxy agents and bilingual network management systems. Proxy agents. An SNMP v2 agent can act as a proxy agent on behalf of SNMP v1 managed devices as follows. A SNMP v2 NMS issues a command intended for an SNMP v1 agent. The NMS sends the SNMP message to the SNMP v2 proxy agent. The proxy agent forwards get, getNext, and set messages to the SNMP v1 agent unchanged. Get bulk messages are converted by the proxy agent to getNext messages and then are forwarded to the SNMP v1 agent. The proxy agent maps SNMP v1 trap messages to SNMP v2 trap messages and then forwards them to the NMS. Bilingual Network Management System. Bilingual SNMP v2 network management systems support both SNMP v1 and SNMP v2. To support this dual management environment, a management application in the bilingual NMS must contact an agent. The NMS then examines information stored in a local database to determine whether the agent supports SNMP v1 or SNMP v2. Based on the information in the database, the NMS communicates with the agent using the appropriate version of SNMP. SNMP version 3 adds security to the 64-bit counters. SNMP version 3 adds both encryption and authentication, which can be used together or separately. Setup is more complex than just defining a community string, but if we require security, this is the way to do it. SNMP v3. SNMP v3 is defined by RFC 3411, RFC 3418. SNMP v3 primarily added security and remote configuration enhancements to SNMP. SNMP v3 is the current standard version of SNMP. The IETF has designated SNMP v3 a full Internet standard, the highest maturity level for an RFC. SNMP v3 looks much different by introducing new textual conventions, concepts, and terminology and cryptographic security. SNMP v3 includes three important services: authentication, privacy, and access control. SNMP v3 abandons the notion of managers and agents. Both managers and agents are now called SNMP entities. Each SNMP entity contains one SNMP engine and one or more SNMP applications. These new concepts are important because they define architecture rather than simply a set of messages. The architecture helps to separate different pieces of SNMP system in a way that makes a secure implementation possible. SNMP version 3 adds security to the 64-bit counters. SNMP version 3 adds both encryption and authentication, which can be used together or separately. Setup is more complex than just defining a community string, but if we require security, this is the way to do it. SNMP v3 Security Model. SNMP v3 security model is developed to protect the following security threats. Modification of information, contents modified by unauthorized user. Masquerade, change of originating address by unauthorized user. Message stream modification, reordering, delay, or replay of messages. Disclosure, eavesdropping. SNMP v3 provides important security features. Message integrity to ensure that a packet has not been tampered with in transit. Authentication to verify that the message is from a valid source. Encryption of packets to prevent snooping by an unauthorized person. USM and VASM. SNMP v3 architecture introduced a user-based security model or USM for message security and the view-based access control model or VACM for access control. USM uses the concept of a user for which security parameters, for example levels of security, authentication and privacy protocols and keys, are configured at both the agent and the manager. Messages sent using USM are better protected than messages sent with community-based security, where passwords are sent in the clear and can be displayed in traces. With USM, messages exchanged between the manager and the agent have data integrity checking and data origin authentication. User-based security model USM. It was proposed in RFC 2274 and it describes the user-based security model for SNMP v3. It defines the elements of procedure for providing SNMP message level security. The USM protects the user against 4 threats, which are modification of information, masquerade, message stream modification, disclosure that is optional. The USM uses MD5, that is message digest algorithm, and the secure hash algorithm to provide data integrity, to directly protect against data modification attacks, to indirectly provide data origin authentication, and to defend against masquerade attacks. It also uses data encryption standard or DES to protect against disclosure. View-based access control model or VACM. It was proposed in RFC 2275 and it describes the view-based access control model for SNMP v3. It defines the elements of procedure for controlling access to management information. The VACM is simultaneously be associated in a single engine implementation with multiple message processing models and multiple security models. The document also includes a MIB for remotely managing the configuration parameters for the view-based access control model. SNMP architecture. An SNMP engine provides services for sending and receiving messages, authenticating and encrypting messages, and controlling access to managed objects. There is a one-to-one association between an SNMP engine and the SNMP entity which contains it. Within an administrative domain, an SNMP engine ID is the unique and unambiguous identifier of an SNMP engine. Since there is one-to-one association between SNMP engines and SNMP entities, it also uniquely and unambiguously identifies the SNMP entity within that administrative domain. Note that it is possible for SNMP entities in different administrative domains to have the same value for SNMP engine ID. The engine contains number 1, a dispatcher, number 2, a message processing subsystem, number 3, a security subsystem, and number 4, an access control subsystem. There is only one dispatcher in an SNMP engine. It allows for concurrent support of multiple versions of SNMP messages in the SNMP engine. The message processing subsystem is responsible for preparing messages for sending and extracting data from received messages. The message processing subsystem can potentially contain multiple message processing models. For example, one for processing SNMP v1 messages and another for SNMP v2c and yet another for SNMP v3. The security subsystem provides security services such as the authentication and privacy of messages and potentially contains multiple security models. The access control subsystem provides authorization services by means of one or more of access control models. Applications include command generators which monitor and manipulate management data, command responders who provide access to management data, notification originators which initiate asynchronous messages, notification receivers which process asynchronous messages, and proxy forwarders which forward messages between entities. These applications make use of the services provided by the SNMP engine. An SNMP entity containing one or more command generator and or notification receiver applications along with the associated SNMP engine has traditionally been called an SNMP manager. SNMP version 3 or SNMP v3 message format. In the late 1990s, SNMP version 3 was created to resolve the problems that occurred with the many different variations of SNMP v2. The SNMP v3 framework adopts many components that were created in SNMP v2, including the SNMP v2 protocol operations, PDU types, and PDU format. Amongst the significant changes made in SNMP v3 include a more flexible way of defining security methods and parameters to allow the coexistence of multiple security techniques. The general message format for SNMP v3 still follows the same idea of an overall message wrapper that contains a header and an encapsulated PDU. However, in version 3 this concept is further refined. The fields in the header have themselves been divided into those dealing with security and those that do not deal with security matters. The non-security fields are common to all SNMP v3 implementations, while the use of the security fields can be tailored by each SNMP v3 security model and processed by the model in an SNMP entity that deals with security. This solution provides considerable flexibility while avoiding the problems that plagued SNMP v2. The overall SNMP v3 message format is described in RFC 3412, which is described version 3 message processing and dispatching. It is shown in table. And now let's look at the PDU format for SNMP v3. Aha! We are spared this because SNMP v3 uses the protocol operations from SNMP v2. This is described in RFC 3416, which is just an update of RFC 1904. Thus, the PDU formats are the same as in the previous topic. SNMP applications. There are currently 5 SNMP v3 applications defined. This is summarized as command generators, creates SNMP messages, command responders, respond to SNMP messages, notification originators, send trap or inform messages, notification receivers, receive and process trap or inform messages and proxy forwarders, forward messages between SNMP entity components. SNMP v1 protocol. SNMP version 1 or SNMP v1 is the initial implementation of the SNMP protocol. It is described in request for comments or RFC 1157 and functions within the specifications of the Structure of Management Information SMI. SNMP v1 operates over protocols such as User Datagram Protocol UDP, Internet Protocol IP, OSI Connectionless Network Service, that is CLNS, AppleTalk Datagram Delivery Protocol DDP, and Novel Internet Packet Exchange or IPX. SNMP v1 is widely used and is the de facto network management protocol in the Internet community. SNMP v1 easy to set up, only requires a plain text community. The biggest downsides are that it does not support 64-bit counters, only 32-bit counters, and that it has little security. A community string sent in plain text, possibly from a restricted range of allowed IP addresses, is as good as the security gets. In other words, no security from someone with access to the network. Such a person will be able to see the community string in plain text, and spoofing a UDP packet source IP is trivial. SNMP1 and Structure of Management Information SMI. The structure of management information or SMI defines the rules for describing management information using abstract syntax notation 1 ASN.1. The SNMPv1 SMI is defined in request for comments or RFC 1155. The SMI makes three key specifications: ASN.1 data types, SMI specific data types, and SNMP MIB tables. SNMP-V1 and ASN1 data types. The SNMP-V1 SMI specifies that all managed objects have a certain subset of abstract syntax notation 1 or ASN.1 data types associated with them. Three ASN.1 data types are required: name, syntax, and encoding. The name serves as the object identifier or object ID. The syntax defines the data type of the object, for example, integer or string. The SMI uses a subset of the ASN.1 syntax definitions. The encoding data describes how information associated with a managed object is formatted as a series of data items for transmission over the network. SNMPv1 protocol operations. SNMP is a simple request response protocol. The network management system issues a request and managed devices return responses. This behavior is implemented by using one of 5 protocol operations which are described below. GET request, used by the manager to request a specific MIB variable from the agent. GET next request, used after the initial GET request to retrieve the next object instance from a table or list. SET request, used to set a MIB variable on an agent. GET response, used by an agent to respond to a manager's GET request or GET next request message. Trap, used by an agent to transmit an unsolicited alarm to the manager. A trap message is sent when specific conditions occur, such as a change in the state of a device or component failure, or an agent initialization or restart. SNMPv1 message formats. SNMP1 messages contain two parts, a message header and a protocol data unit. This is shown below. Message header, PDU or protocol data unit. SNMPv1 message header. Version number, community name, PDU or protocol data unit. SNMPv1 message headers contain two fields, version number and community name. The following descriptions summarize these fields. Version number specifies the version of SNMP used. Community name. This is an SNMP password. Management stations and management agents must use community names that match, otherwise frames will be discarded. The SNMP community name is not encrypted. Protocol data unit PDU indicates SNMP operation and variable bindings. SNMPv1 protocol data unit PDU. SNMPv1 PDUs contain a specific command, that is get, set, and so on, and operands that indicate the object instances involved in the transaction. SNMPv1 PDU fields are variable in length, as prescribed by abstract syntax notation 1 or ASN.1. Figure illustrates the fields of the SNMPv1 PDU. PDU type, request ID, error status, error index, var, bind, list. PDU type is an integer. The various PDU types values are shown below. PDU type, an integer value that indicates the PDU type. Table, first column, PDU type value, second column, PDU type. First row, under first column, 0, under second column, get request PDU. Second row, under first column, 1, under second column, get next request PDU. Third row, under first column, 2, under second column, get response PDU. Fourth row, under first column, 3, under second column, set request PDU. Request ID associates SNMP requests with responses. Error status indicates the number of errors and error types. Only the response operation sets this field, otherwise it remains to 0. An integer value that is used in getResponse PDU tells the requesting SNMP entity result. A value of 0 indicates that no error has occurred. The other values indicate what sort of error happened. This is described in the table given below. Error status value, error code, description. 0, no error occurred. 1, too big, the size of getResponse-PDU would be too large to transport. 2, no such name. The name of the requested object was not found. 3. Bad value. A value in the request did not match the structure of the recipient object. For example, an object in the request was specified with an incorrect length or type. 4. Read only. An attempt was made to set a variable that has an access value indicating that it is read only. 5. Gen error. An error other than one of the preceding 4 types that has occurred. Error index associates an error with a particular object instance. Only the response operation sets this field. Other operations set this field to 0. Variable bindings. It has a list of variable ID and variable value pairs as indicated in the figure below. Variable ID. This contains the object identifier of the variable defined in the Structure of Management Information or SMI specification. Variable value. This contains the value of the variable. Trap PDU format. The SNMPv1 trap PDU consists of 8 fields. Illustrates the fields of the SNMPv1 trap PDU is shown below. The following descriptions summarize the fields illustrated in above figure. Enterprise identifies the type of managed object generating the trap. Agent address provides the address of the managed object generating the trap. Generic trap type indicates one of a number of generic trap types. Specific trap code indicates one of a number of specific trap codes. Timestamp provides the amount of time that has elapsed between the last network reinitialization and generation of the trap. Variable bindings, the data field of the SNMPv1 trap PDU. Each variable binding associates a particular object instance with its current value. SNMPv1 easy to set up, only requires a plain text community. The biggest downsides are that it does not support 64-bit counters, only 32-bit counters, and that it has little security. A community string sent in plain text, possibly from a restricted range of allowed IP addresses, is as good as the security gets. In other words, no security from someone with access to the network. Such a person will be able to see the community string in plain text, and spoofing a UDP packet source IP is trivial. STD Management Information Base (MIBs). A Management Information Base or MIB is a collection of information that is organized hierarchically. MIBs are accessed using a network management protocol such as SNMP. They are comprised of managed objects and are identified by object identifiers. A managed object, sometimes called MIB object, an object or a MIB, is one of any number of specific characteristics of a managed device. Managed objects are comprised of one or more object instances which are essentially variables. Two types of managed objects exist, scalar and tabular. Scalar objects define a single object instance. Tabular objects define multiple related object instances that are grouped in MIB tables. An example of a managed object is at input, which is a scalar object that contains a single object instance, the integer value that indicates the total number of input AppleTalk packets on a router interface. An object identifier or object ID uniquely identifies a managed object in the MIB hierarchy. The MIB hierarchy can be depicted as a tree with a nameless root, the levels of which are assigned by different organizations. The top-level MIB object IDs belong to different standards organizations, while lower-level object IDs are allocated by associated organizations. Vendors can define private branches that include managed objects for their own products. MIBs that have not been standardized typically are positioned in the experimental branch. The managed object at input can be uniquely identified either by the object name ISO.identified organization. The MIB tree illustrates the various hierarchies assigned by different organizations. The SNMPv1 SMI defines highly structured tables that are used to group the instances of a tabular object, that is, an object that contains multiple variables. Tables are composed of 0 or more rows which are indexed in a way that allows SNMP to retrieve or alter an entire row with a single get, getNext, or set command. MIB file format. A MIB file is just ASCII text so that it can be viewed in any word processor or text editor such as Microsoft Notepad. Some manufacturers provide pre-compiled MIBs in binary format, but those aren't readable. In such situation, raw ASCII version of the MIB file is required. MIB files are sometimes provided as Unix text files. Unix text format is significantly different from DOS or Windows text format. If we want to view MIB files on a Windows PC, we have to get from vendor a DOS formatted version, or conversion utility software can be used to convert between text formats. The MIB is written in ASN.1 notation, Abstract Syntax Notation 1. ASN.1 is a standard notation maintained by the ISO, that is International Organization for Standardization, and used in everything from the World Wide Web to aviation control systems. For our purposes, there are only a few things to understand about ASN.1. Number 1. It's human readable. Number 2. It's specifically designed for communication between dissimilar computer systems, so it's the same for every machine. Number 3. It's extensible, so it can be used for describing almost anything. Number 4. Once a term is defined in ASN.1, it can be used as a building block for making other terms. This is very important for understanding MIB structure. MIB2 RFC standards are applied to all SNMP v1 agent entities. The following RFCs are a part of MIB2. RFC 1213 Management Information Base for Network Management of TCP/IP based Internets MIB2. RFC 2863 The Interfaces Group MIB IF. RFC 3418 Management Information Base or MIB for the Simple Network Management Protocol or SNMP. RFC 4001 Textual Conversions for Internet Network Addresses. RFC 4022 Textual Conversions for Internet Network Addresses TCP. RFC 4113 Management Information Base for the User Datagram Protocol UDP. RFC 4292 IP Forwarding Table MIB IP Forward. RFC 4293 Management Information Base for the Internet Protocol or IP. RFC 4898 TCP Extended Statistics MIB TCP eStats. Structure of Management Information. SNMP Simple Network Management Protocol. The Simple Network Management Protocol SNMP is an application layer protocol that facilitates the exchange of management information between network devices. It is a part of Transmission Control Protocol / Internet Protocol or TCP/IP protocol suite. SNMP enables network administrators to manage network performance, find and solve network problems, and plan for network growth. Two versions of SNMP exist: SNMP version 1, SNMP v1, and SNMP version 2 or SNMP v2. Both versions have a number of features in common, but SNMP v2 offers enhancements such as additional protocol operations. Standardization of yet another version of SNMP, SNMP version 3 or SNMP v3 is pending. This article provides descriptions of the SNMP v1 and SNMP v2 protocol operations. SNMP facilitates the exchange of network information between devices and a basic network management. An SNMP managed network consists of three key components: managed devices, agents, and network management systems or NMS. A managed device is a network node that contains an SNMP agent and that resides on a managed network. Managed devices collect and store management information and make this information available to NMS using SNMP. Managed devices, sometimes called network elements, can be routers and access servers, switches and bridges, hubs, computer hosts, or printers. An agent is a network management software module that resides in a managed device. An agent has local knowledge of management information and translates that information into a form compatible with SNMP. An NMS executes applications that monitor and control managed devices. NMS provide the bulk of the processing and memory resources required for network management. One or more NMS must exist on any managed network. An SNMP managed network consists of managed devices, agents, and NMS illustrates the relationships of these three components. SNMP must account for and adjust to incompatibilities between managed devices. Different computers use different data representation techniques, which can compromise the capability of SNMP to exchange information between managed devices. SNMP uses a subset of Abstract Syntax Notation 1 or ASN.1 to accommodate communication between diverse systems. Structure of Management Information SNMP v1. SNMP version 1 or SNMP v1 is the initial implementation of the SNMP protocol. It is described in Request for Comments or RFC 1157 and functions within the specifications of the Structure Management Information or SMI. SNMP v1 operates over protocols such as User Datagram Protocol or UDP, Internet Protocol or IP, OSI Connectionless Network Service or CLNS, AppleTalk Datagram Delivery Protocol or DDP, and Novel Internet Packet Exchange or IPX. SNMP v1 is widely used and is the de facto network management protocol in the Internet community. SNMP v1 and Structure of Management Information. The Structure of Management Information or SMI defines the rules for describing management information using Abstract Syntax Notation 1 or ASN.1. The SNMP v1 SMI is defined in RFC 1155. The SMI makes three key specifications: ASN.1 data types, SMI specific data types, and SNMP MIB tables. SNMP v1 and ASN.1 data types. The SNMP v1 SMI specifies that all managed objects have a certain subset of Abstract Syntax Notation 1 or ASN.1 data types associated with them. Three ASN.1 data types are required: name, syntax, and encoding. The name serves as the object identifier or object ID. The syntax defines the data type of the object, for example, integer or string. The SMI uses a subset of the ASN.1 syntax definitions. The encoding data describes how information associated with a managed object is formatted as a series of data items for transmission over the network. SNMP v1 and SMI specific data types. The SNMP v1 SMI specifies the use of a number of SMI specific data types which are divided into two categories: simple data types and application-wide data types. Three simple data types are defined in the SNMP v1 SMI, all of which are unique values, integers, octet strings, and object IDs. The integer data type is a signed integer in the range of -2147483,648 to 2147483,647. Octet strings are ordered sequences of 0 to 65535 octets. Object IDs come from the set of all object identifiers allocated according to the rules specified in ASN.1. 7 application-wide data types exist in the SNMP v1 SMI: network addresses, counters, gauges, time ticks, opaques, integers, and unsigned integers. Network addresses represents an address from a particular protocol family. SNMP v1 supports only 32-bit IP addresses. Counters are non-negative integers that increase until they reach a maximum value and then return to 0. In SNMP v1, a 32-bit counter size is specified. Gauges are non-negative integers that can increase or decrease but that retain the maximum value reached. A time tick represents a hundredth of a second since some event. An opaque represents an arbitrary encoding that is used to pass arbitrary information strings that do not conform to the strict data typing used by the SMI. An integer represents signed integer valued information. This data type redefines the integer data type, which has arbitrary precision in ASN.1 but bounded precision in the SMI. An unsigned integer represents unsigned integer valued information and is useful when values are always non-negative. This data type redefines the integer data type, which has arbitrary precision in ASN.1 but bounded precision in the SMI. SNMP MIB tables. The SNMP v1 SMI defines highly structured tables that are used to group the instances of a tabular object, that is, an object that contains multiple variables. Tables are composed of 0 or more rows, which are indexed in a way that allows SNMP to retrieve or alter an entire row with a single get, getNext, or set command. SNMP v1 protocol operations. SNMP is a simple request/response protocol. The network management system issues a request and managed devices return responses. This behavior is implemented by using one of four protocol operations: get, getNext, set, and trap. The get operation is used by the NMS to retrieve the value of one or more object instances from an agent. If the agent responding to the get operation cannot provide values for all the object instances in a list, it does not provide any values. The getNext operation is used by the NMS to retrieve the value of the next object instance in a table or a list within an agent. The set operation is used by the NMS to set the values of object instances within an agent. The trap operation is used by agents to asynchronously inform the NMS of a significant event. Conclusion. In this chapter, we have covered the following in detail: Simple Network Management Protocol, SNMP v1, Structure of Management Information, STD Management Information Base or MIBs, SNMP v1 Protocol, SNMP v2, SNMP v3, Network Management Functions, Fault Management, Fault Identification and Isolation, Event Correlation Techniques. Network Management Functions, Accounting and Performance, Accounting Management, Performance Management, Network Usage, Metrics and Quotas. Remote Network Monitoring, RMON, Remote Network Monitoring, etc.